So thank you very much. So at last year's JuliaCon, I started with an example showing our package, example simulation showing the breaking of spaghetti. So for this year, I thought maybe I will start with a similar example from the kitchen you can all try out at home. So basically what you can see here is a simulation we've done with our package on glass falling to the ground and breaking into many pieces. So let me comment this with a saying from my wife's grandfather: falling is not a problem, but hitting the ground is. And this is especially true when you want to simulate that with a numerical framework, because it's very hard to obtain all these different fracture elements, and yeah, it's very hard. But with Peridynamics you can do that. It's very suitable and very suited for these kind of dynamic fracture simulations. So what is my talk about? I want to start with a short introduction. What is Peridynamics? So introduce you to the main equations. And then I want to go on with what is our Peridynamics package and introduce that a little bit if you don't know it currently. And then I want to focus on the API improvements, so basically the public user interface, and then also on recent performance improvements we've made. So basically the internal side of the package. So to begin with, what is Peridynamics? It's basically a non-local formulation of continuum mechanics. Basically the body is discretized often by points, but it could in theory also be discretized by a mesh. But it's a non-local method, so these points interact only inside a specific horizon, so inside of a specified radius around a root point. So basically when you model in kinematics with that framework, it's basically you look at these interactions, these bonds. Here you can see it as x and x prime. So to introduce a little bit notation, if you want, you look at the deformation. Like in classical continuum mechanics, you refer to the reference configuration at, so basically the time step 0, and then at the current configuration, the deformed body. And if you look at reference position coordinates, you refer them as with uppercase letters, capital X, and in the current position with lowercase letters. So basically, the main equation we solve is the equation of motion from Peridynamics. You have here the density, the acceleration, and the internal and external force densities. And in this internal force density is very important because many different formulations exist that differ regarding that. So the different material formulations differ in regards of the calculation of this internal force density. So if you want to calculate that, basically you have to look at these force vector states you can see on the right side of the picture. Basically T and T prime. These are mainly then differently calculated in the different backends or different formulations of Peridynamics. They can be of the same value and in opposite direction for bond-based Peridynamics, but that is not the case for ordinary or non-ordinary state-based Peridynamics. What I just want to say with this slide is there are many different implementations of Peridynamic formulations, and it's very difficult to implement them. It's not the same way. And basically that was the main motivation for me to use Julia for writing Peridynamic simulations, because it was much easier to implement these different approaches. So what is Peridynamics.jl? It's a registered Julia package. You can see the GitHub page with this QR code, and it's purely written in Julia. So basically the goals of this package are mainly to make Peridynamic simulations accessible for a broader user base. And for me it was also a reason to implement these, because new material models was very hard to implement for me, and it could be made easier for other people too if there's a Julia package. There are also packages out there in C++ or other languages, but they're very hard to use. And you can write Julia code to obtain a simulation with this package. So I want to show a short usage example. So this is a very common example or simulation in mechanical engineering. You have this tensile test specimen, which then is subjected to tension at the bottom and the top. And basically, you can use just these lines of code for a simulation with our package. Here, you first construct a body, and then at this body, you specify the material formulation. Currently, 4 formulations are available in our package. And what you can do then, you can import abacus measures into the simulation. Then the element will be converted to a point. You can specify material parameters to that body, then boundary conditions, and actually you can define element sets inside of abacus, and these sets will be recognized and converted to point sets here in the package. So you can specify the boundary conditions using these sets, and then you specify a solver and can obtain simulation results with submit job. So basically, if we look at the simulation here, it's what we would expect. This specimen is subjected to tension, and in the middle of the specimen there a crack is forming. So this is basically a dynamic simulation with fracture involved, but you can also do a different kind of simulation with just a few changes. This is a different setup, so basically the same point cloud, the same spatial discretization, but with different conditions. So we have here force density conditions. Basically, we apply a constant force at the top and the bottom, and we disallow failure, so failure should not occur in the model, and we use other solver. And if we look at the simulation here, you can see it's with just a few changes we obtained a quasi-static simulation, just the elongation of this specimen under load. So basically, these things are implemented. What I showed you are the current version. If we compare it to the previous version, it was much more code, but everything was a separate struct in the previous version. So the material was a separate struct, the boundary conditions were a struct, settings, and also the analysis. And then at the end, all these things would get bundled up together for a job to submit. In the current version, it's a little bit different. So it's not just only less code, and I think, in my opinion, a little bit easier to read. So methods add something to a struct. So this allows us to write more meaningful error checks. I will show you that here. So basically that's an old code, and we introduce an error purposefully. So we introduce here a boundary condition that references point ID 1001, but with a body that only has 1000 points. So basically when you construct or bundle these things up, this would be the first time this error could be detected. But because if you disallow bound checking, the simulation will also run completely, but then you will get NaN values. And I ended up helping our students a lot of times searching for errors in the user input. So we improved that. In the current version, you can only add things via a point set. And if you try to add a point set for points that are not there, there's immediately an error, because we already know when specifying these point sets, adding these into the body, that there are not more than 1000 points. So basically, if a job can be created, it is likely that it will run without input errors, because per user error. So every possible check is done as early as possible. So there's a new setup. It's a bit lagging on my computer. So there's a new type of setup for these simulations. Basically, you first construct a spatial setup. So basically, for single body simulations, you just create a body object and add everything that also is dependent or important for that body. After that, you add a abstract time solver. Basically, currently 2 are implemented. And then these things get bundled up to a job. So, and for multi-body simulations, this even helps because it was a mess in the previous version. You needed a lot of intermediate structs, but now you can construct the bodies at the same you would do for a single body simulation, and these will get bundled up to a multi-body setup. Then you add the contact, just do that setup. And then again, you specify a solver, and it will get bundled up for a job. So now we will focus more on the performance, or basically the internals. That was kind of the user interface, but how do we use parallel simulations? So if we use that same example, it's basically, you can run that on parallel using multiple threads. You just have to start Julia with more than one thread, and then it will automatically run on multiple threads. But what you also can do now with the current version, you just can run it, put it in a script, and run that script with MPI, and without any code changes, the simulation will run with MPI. So basically, the parallel backend is automatically detected, and then the backend will be used for the simulations. So what is the performance of that? So performance was always a thing for this package in the previous version, but let me introduce a short benchmark I always use. I don't want to go in detail on how this code works. You can basically copy that and try it out on your machine. So basically that are 1,000 points or 100,000 points for this setup, and the simulation completes after roughly 20 seconds on my machine. But the main thing, how is the HPC performance of the package? So if you look at the speed up of the previous version, the multithreading in version 0.2, basically what you can see in this plot is my realization that parallel processing on an HPC system is not just add threads to a for loop. It's much more complicated than that. So why was this slow? Here you can see the important code, the bottleneck of the simulations, the force density computation. And in the previous version, basically what we did was we looped parallel over all threads to create a thread ID, and then had a pre-partitioned bond vector array that contained all bonds for this thread. And then this internal force density, BINT, is basically a 3-dimensional vector and array, and each thread writes on its own dimension. So, and then after that, we would need a reduction. The error with that is force sharing. So I think there are a lot of people here at JuliaCon who could explain that better than me. But basically, because all threads use the same array here, the cache line will get updated for every thread if something is written in that. And therefore, that's a small overhead. So we basically need a new data structure for our data to be stored. And what we did, we completely redesigned the package. So basically, under the hood, nothing is, not a single function was the same in the previous version. So now we use a body and split this body apart into body chunks. So what you can see here is basically then we need communication. So we have these local points that are local to the body chunk, but also some points of the other chunk. Here you can see the green and blue interface points, the halo points, are needed for that chunk for the computation. So basically then you need communication. There are two types, basically local to halo communication. So data that is calculated on here, the local points, needs to be updated into the halo area of another chunk. And also the other way around, so halo to local exchange. So data that is calculated on the halo points, just in the simulation, the index j, that data has to be then exchanged to the other local points of the other body chunk. So basically, this needs communication, but the same approach is used for multithreading and MPI in our package. So everything happens on a body chunk. This is basically the type that makes it possible to write these two backends without writing everything for two versions of the package. So basically, the body chunk contains material information. That is mainly the material formulation type, which can be used for multiple dispatch. Then the point parameters, like the density, Young's modulus, post-source ratio, and other material parameters that can differ for each point. And then a system with all reference configuration informations, the neighbor informations, and a storage, which then is basically everything that will change during the simulation. So displacement, velocity, acceleration, and so on. So this allows reusing methods that work on a body chunk with multithreading and with MPI, because they both use this type. So then we need a threads or a MPI data handler. Basically, a threads data handler contains multiple body chunks. And then you need halo exchange information. And compared to that, an MPI data handler only has one body chunk, but also needs the same halo exchange information and additionally some MPI stuff. So basically, the core functions that or core methods on these body chunks or halo exchanges can be reused with both backends. So how does this internal structure change the HPC performance? You can see the scaling of multithreading in the current version was greatly improved, and not only because of this data structure, but also strongly because of thread pinning. It's a great package to pin threads to specific cores or NUMA domains on a cluster. You can look it up. There was a great talk at last year's JuliaCon. It's a package from Carsten Bauer. And if you look at the MPI simulation, it scales very well. So if you look at the highest point here, it's roughly 800,000 points, and with 46 MPI ranks, that simulation will take only 65 seconds. So basically, this wouldn't be possible without the help of the Partmann Center of Parallel Computing. So I really want to acknowledge the support of Carsten Bauer and Jin Wu, who invited me to a hackathon, and there we created the basic foundations, the core concepts on how this package can improve the parallel performance. So a little bit different is the performance for multi-body simulations, because there you have additional things that needs to be considered, because if these bodies move, then you need a contact search algorithm, because these points are not always in contact. And if these points are nearer to another or are lower than a specific radius, then there's a contact. And to obtain these information, it's important that you have an updated neighborhood search. And here I want to acknowledge especially the Trixie Particle guys who wrote a very nice package. There was also a talk on that on Wednesday, so you can check that out on YouTube. And it really helped me to obtain performance increase in these kind of simulations. So if we look at the benchmark, the old Peridynamics logo, this took, in the previous version on my computer, around 115 seconds. And now it only takes around 23 seconds, just because of these internal changes and also the updated neighborhood search. But keep in mind, it's currently only available for multi-threading support, so it's work in progress to add MPI support for this in the future. So things that can be improved further. So basically, the spatial decomposition is currently very trivial. We don't have a suitable decomposition algorithm yet. That would be a thing that could improve MPI performance very much. Additionally, other material models will be a nice add-on that that don't have the pitfalls of the current models implemented. And also a thing currently only, I think for package developers or for me, it's easier to implement new models because there is no public API for defining new material models. And it would be very nice to have public macros to define a new model. Under the hood, in the internals, I already use some of these macros. So this is basically a copy from the current source code. If we create a storage for a specific material and a specific solver, you can specify that it belongs to that with this add storage macro. And if you want to specify which fields need an halo exchange, you can do that also with this one line with this macro. So basically improving that and maturing that interface could help to gain a public API in the future. And one more thing, the Trixie Particle guys and we sat together yesterday to try to visualize this class simulation with Blender. So basically they do fluid simulations, and because we are not an expert in Blender, we just had to reuse their material, so it just currently looks like a water glass, but it will likely improve in the future. But the main thing I want to show is they have really great algorithms for improving the point clouds. So basically they helped me yesterday to improve from a cloud looking like that was basically converted from a finite element mesh to a very good point cloud with a smooth boundary or smooth surface. So check out their package, it's really great. So what I think we could add maybe is fluid-solid interaction with Peridynamics. So maybe next year we can show the glass full with wine. So with that, I want to end my talk, and thank you very much for your attention.
Any questions?
Could you explain a bit more on why there's a difference in performance of multi-thread and MPI stuff, since I don't really get it.
So you basically want why there's a performance difference here in... Okay, so I think this could be related to many things. It's very sensitive to the setup of the parallel of the setup on the cluster. So I once had a simulation where I just included a recursive remove of previous results, and that would change the it completely. So actually, I'm not very sure about the details of that. It could be setup, but it could also be just because they are under the hood completely differently using the communication. One is via the MPI interface, and the other approach is using basically just at this point information to that into the same vector. So maybe that would be the reason, but I think I'm not very good at explaining that because I'm more at the application side of using Julia, not on the HPC setup expert side. So maybe that's a good question for some people of the HPC community, but I'm not quite sure. Yeah.
Thank you.
Very great talk, thank you. You showed your benchmark setup, like displayed, and then also your MPI results, like it took about 50 seconds for 800,000 particles.
Yes.
So how many time steps did you simulate?
At each time, I fixed the number to 2,000 time steps.
Ah, okay.
So to compare basically the implementation, I think with 800,000 points, I probably would need more time steps to see the same simulation results, because if we have increase the number of points, the time step you would need for the velocity Vallée solver also decreases. So you need more time steps to cover the same time interval of the simulation. So, but this simulation results with MPI on the cluster were obtained by just with 2,000 time steps.
Cool, thank you.
Other questions? Thank you.